coterminal. How is this practical? How is this practical? Yeah, exactly. So if I was to be an angle in standard position or moving an angle in standard position, I'll do it from your perspective, okay? If I was to move 45 degrees, from your perspective, here's the positive x-axis. If I was to move 45, I could go right here, right guys? 90 would be like up here, so I'm over here, 45-ish, yeah? But what's another way that I could end in the exact same, or at least, because I'm not being very precise, but is there another way that I could end in the exact same or a similar location or ending position? How else could I get there? Clockwise. 315 degrees. Okay, that's one way. And I'm in the same exact, pointing the same exact direction. What's another way that I could get there? I could move counterclockwise 45. I could move clockwise 315. What else could I do? Counterclockwise. But I'm back to where I started. That was 360. Oh, keep going 45. So that would be, how do I do that? I would do 360 plus 45, or better, 45 plus 360, right? How else could I end there? I can turn 2 rounds, yeah. So if I do 1, there's 360. If I do 2, that's 720. Feels like that whole spinning game. And then another 45, right? So that'd be 720 plus 45, or 45 plus 720. But hold on. The point isn't so much, I mean, it is to learn these new words, but you guys should have learned these words before: coterminal angle, sharing a terminal side that we wrote down earlier. But I also want you to get used to radians. Pause. 360 degrees is how many radians again? 2 pi. Okay, so what if I was to give you something like, find a positive and negative coterminal angle. What if I was to give you something like 3 pi over 4? That's the location that I'm talking about. Wait a minute, why does it make sense that 3 pi over 4 is over here? What are we corresponding, or what are we relating pi to? Made you all hungry yesterday? What was I relating pi to? Calzones. Calzone, half circle, 3/4 of a calzone. Isn't that like cut into fourths and then, 1, 2, 3 pieces, right? So 3 pi over 4 gets right over here in the second quadrant. There's my angle, 3 pi over 4. What's another way of getting there? Well, hold on. Let me go ahead and cut both of my calzones, because I have 2 of them to make a whole circle. I'm going to cut them into fourths. So take my calzone, my pi, cut it into half again, cut it into half again, right? So I have 3 of them, and that's one way of getting there. What's another way of getting there? How could I get a positive coterminal angle, aka also moving in the counterclockwise position? I could turn more. Now, couldn't we say just add 2 pi, right? So we could just say, oh, no big deal, just add 2 pi, so 3 pi over 4 plus 2 pi. But some of you are like, ugh, fractions, I hate fractions. And you're so paranoid about fractions, and it's really quite sad, because you use fractions all the time. Why would 8 pi over 4 be way easier than 2 pi? Now, could you mathematically have done the whole, like, 2 pi over 1, I need common denominators, so times 4 over 4, and then you can go ahead and do 3 pi plus 8 pi all over 4. And yeah, you could do that. You could do that. Or you could have come back here and been like, wait a minute. Couldn't you have just added 8 pi over 4 to begin with? Because if you're adding 2 pi, if you're adding 2 calzones and everything's cut into fourths, wouldn't that be 8 slices? Right? So what's a positive coterminal angle in radians? Well, we could say one coterminal angle, let's name him alpha, because the original one was like the theta, right? Alpha could be, well, we already can see, hopefully, 11 pi over 4. How could you get there going not a positive direction, but going a negative direction? So positive direction, we can go ahead and turn 8 pi over 4, and then that extra 3 pi over 4. So 2 pi plus another 3, or 8 pi over 4 plus another 3 slices. What are we going to do to go negative? Trying to get the air going because some of you guys desperately need it. To get negative. Joe, just a moment ago when I said like, oh, hey, 45, was like, oh, hey, negative 315. But how do you figure that out? going backwards from the 45, subtracting 360. So we could do the same thing. We could start at 3 pi over 4, and we could go backwards 360, which is the same thing as doing, well, a negative angle that's a little bit less than 360. But the math would say, well, why don't you take that 3 pi over 4 and subtract 2 pi? And some of you guys are like, ugh, fractions. Hold on, we're talking about fourths. So how many fourths is 2 pi again? Yeah, you could just subtract 8 pi over 4. So then my beta, which is another coterminal angle, could be negative 5 pi over 4. And maybe some of you are starting to do this a little bit more mental math style in the sense of, if that's positive 3 slices, that would be negative 4 in another, negative 5 slices. But this top one, you just kind of had to add 8 slices to get back to there. But basically what we're doing is up here, we're just realizing that every time you turn a multiple of 2 pi, which is going to be the same thing, you guys are right, for those of you that think in degrees still, of 360s, multiples of 360s, you are going to end back where you started. And that brings us to the definition down below. The definition down below, I'll show it with degrees and radians. Let me zoom in just a little bit. I'll show it with degrees and radians. Hold on. What letter is this? That's a Greek letter, right? Ah, look at your alphabet. What Greek letter is it? Look at your alphabet. No, not theta. Theta is this guy. Not alpha. That's that guy. Not beta. This is phi. Phi, phi, pho, phum. Phi. Just another letter. Big deal. But if we're talking, our book likes to use phi. I like alpha and beta better. If and only if one angle measure needs to be the original angle measure plus or minus multiples of 2 pi. But it has to be full 2 pi. Not full 2 pi's, you won't land back where you started. You have to do a full revolution to get back. So maybe another hint that we could say is 1 revolution, which is 1 full turn, is going to be turning 2 pi radians. You can put that in parentheses over to the side, just in case we ever need to build a bridge with revolutions and radians. 1 revolution is 2 pi radians. So we can 1 full revolution in the positive counterclockwise, or 1 full revolution way. And yes, we could also say beta plus 3. Multiples of 360 is we need to make sure what our angle is in. This one is only appropriate, the only way of solving when you're in radians is only degrees. Yeah? And real quick, we can just say that is equal to, here we go, any positive integer. So you could add 2 pi, you could add 4 pi. If you want to be a stinker, you can add 24 pi and be like, haha, it lands in the same spot. And I would have to agree. Now, complementary, supplementary. You guys remember these words, kind of, don't you? Complementary, 2 angles, 2 positive angles. 2 angles or 2 positive angles that add up to be what? Do you guys remember? Which one's which? Yes. Supplementary adds up to be 180, whereas complementary adds up to be, yeah. So 2 positive angles. I could name them like with Greek letters, but I won't. 2 positive angles whose sum is 90 degrees. Oh, wait. We're supposed to be getting ready or used to radians. 90 degrees. How much of a calzone is 90? Isn't that half a calzone? Cool. Pi over 2. And then angles. Careful. If I were you, would underline the word positive, because if you have to go negative to make it work, it's illegal, and there is none. There are some angles that don't have complements or supplements. Don't have complements. Positive angles whose sum, as Matthew said, is 180, or how much of a calzone is 180? Whole. Right? The whole half circle. So if it helps, I mean, I guess I could do a little baby notation. I guess. 2 angles are supplementary if and only if alpha plus beta is equal to, wait, we're trying to get used to radians, not degrees. pi. And then two angles are complementary if alpha plus beta is equal to pi over 2. So let's see. What if I was to give you something like, let me color code it. Let's do A. Theta is equal to pi over 3. We're going to do two different ones, looking for the complement and the supplement. I'm just going to put a little c and a little s. And then we're also going to do theta is equal to 5 pi over 6. Complement, supplement. If you think you know what it is, perfect. Go ahead and just write it down and do the work yourself. But if you're like, I'm not quite so sure what we're doing, that's okay. So let's talk about it. Let's talk about it. Pi over 3. Where is he? Is he greater than 90 or less than 90? Wait, stop. Don't think about it. A calzone. Where's a third of a calzone? Where's one of those thirds? Okay. So there's pi over 3. Complement says we need to get all the way from pi over 3 from this angle. Complement says if this is your theta, we need to keep on going to get to 90. Is there an angle there? Yes or no? Yeah. What angle is it? If I need two angles to add up to pi over 2, how could you solve for one? Couldn't you do pi over 2 minus? Right? So technically, if we're doing little baby equations, for complementary, we could do pi over 2 minus, and for supplementary, we could do pi minus. For complementary, we could do pi over 2 minus, and for supplementary, we could do pi minus. We can subtract one from each of the sums, what they're supposed to add up to find the other. So in this first one, we're doing pi over 2 minus my angle, minus theta, which is pi over 3. Aw, fractions. Yeah, it's really hard to think of pi over 3 and pi over 2 together because they have different denominators. You know what's easier to think of? And we'll see this in section 4.2 when we get back. Instead of thinking in thirds, it's actually usually easier to think in sixths. And here's why. How many sixths? 3, 2. Now, when we fill in our unit circle, we don't leave it 3 pi over 6. We think about it as pi over 2 because that's the nice and reduced form. Same thing here. But this kind of helps us with our pi over 6, our other special. That's 4.2. But anyway, long story short, what's in between 3 pi over 6 and 2 pi over 6? If you had gotten common denominators, what's in between them? 1 pi over 6. You could have gotten common denominators and gotten your complement. No big deal. No big deal. Supplementary, though. Supplementary, though, if I was to do pi minus pi over 3, well, hold on. I can kind of think in thirds on this one. Because 1/3 is what I have, and how much is left to get to my whole calzone? If I have 1/3, how do I get to the whole thing? How much is missing if I have 1/3 from the whole? 2/3. But guys, couldn't you have also just gotten a common denominator and subtracted 3 over 3 pi minus 1 over 3 pi is 2 over 3 pi? Totally fine. What, Matthew? That's what I just said. I think you just missed it. I was saying, but couldn't we get common denominators? And common denominators would say 1 whole calzone is 3 over 3. 3 slices out of 3, and 3 over 3 pi is minus 1 over 3 pi is equal to 2 over 3 pi. Or you could say 3 pi over 3 minus pi over 3 is 2 pi over 3, same thing. But yeah, so I'm trying to get you guys thinking in the fractions naturally and not just common denominators, but if worse comes to worse, common denominators are always a great trick. And this one you would have had to multiply by 3 over 3, and this one you would have had to multiply by 2 over 2. There is math that gets you to the exact same spots. Now for this guy, pi over 6, where's he at? 5 pi over 6 is almost a whole calzone. It's all the way over here. So there's my new theta for letter B. What's his complement? Pi over 2 minus. Oh, is it bad if I'm doing 90 degrees minus like 150 degrees? If I'm doing pi over 2 minus something bigger, is that bad? Is there anything left over to get to 90? No. So therefore, there's no complement. The answer would be none. It's past 90. Any angle that's past 90 will not have a complement. Because you can't subtract the 2, pi over 2 minus, you can't subtract and get a positive angle, so it's impossible. But what could I still go to? 180 or pi. So what's left over if I need to do pi minus? Because not only can we think about pi as being 3 pi over 3 or pi as being 4 pi over 4, but we can also think about pi as being 6 pi over 6. It just depends on how many slices I'm cutting it. And if I've cut it into 6 and I have 5 of them, how many is left? 1. So not every angle is going to have a complement and a supplement. Can anybody give me an example of any angle that wouldn't have a complement or a supplement? Both of them would be none. Yeah, 11 pi over 6, 1 and 5/6 of a calzone. Or actually, to be honest, it would be any angle in quadrants 3 and 4. Any angle in quadrants 3 and 4 won't have a complement or a supplement. Any angles in quadrant 2 won't have a complement. Any angle in 1 will have both, because it can go up to 90 and go up to 180. Okay, thinking in fractions, I know it's a little bit messier than supplementary used to be, 180 minus, and complementary used to be 90 minus, but still possible. Let's talk about bridges. If you've ever taken chemistry, you should see the words dimensional analysis and be like, ding, 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 ding. It's a bridge. Don't worry, Lauren, I got you. Grab your notes and a pencil, kiddo. Meet me in the back of the room. It's okay. David likes this. Michael Schweitzer likes this. It works. It works. The nice thing is the 2 pages we took at the beginning of class, we just filled them in. So all you might have missed was filling in those 2 pages. So you can go back and get those and just go to the new one. Okay. We talked about degrees already. Do you guys remember as a fractional part of a circle? Perfect. 1/360th, so awkward, of a circle. Or 1/180th of a semicircle. But that's super awkward. 1 degree being 1/360. Wait, maybe it's not so awkward. If 1 degree is 1/360th of a whole circle, which is 2 pi, that's the same thing as 1/180th of a half circle, which is just pi. So 1/360th of a whole circle, 2 pi, or 1/180th of a half circle, which is pi. Well, pretty quickly we can say, you know what, I think that's going to be my unit or my bridge that I use. Now sometimes you're going to use pi over 180, sometimes 180 over pi. Hopefully I don't have to teach you too much dimensional analysis, because I know Mrs. Leon loves dimensional analysis and building bridges. But the long story of dimensional analysis is you have to memorize. You have to multiply by 1 creatively. But the numbers, hopefully, as we know from chemistry, are not going to be the same. 1 foot does not equal 1 inch. 1 foot is 12 inches, but they are equivalent in their measure, right? So pi and 180, this is 3.1415926, but pi radians is the exact same measure as 180 of those little baby tick marks. Pi radians, the units pi radians, make all the difference. Pi radians equals the same measure as 180 degrees. So if they were to give me some sort of, let's call it like A degrees, Could be 10 degrees, 20 degrees, 37 degrees, 73 degrees. If they were to give me something with a degree mark and they told me or I needed to go to radians, I'm going to have to multiply by, where do I want the 180, on top or on bottom? Come on, make her proud. On bottom, why? I need the degrees to cancel. And what's equivalent to 180 degrees? Pi. Technically, there's a little understood radian. I don't know, super necessary, which it barely ever is. At this point, you go ahead and multiply, simplify the fraction if possible. We don't know what the number a is, so we're not going to go any further. But we don't write a degree mark anymore because now that degree mark is reduced or canceled out, right? And technically, we have this understood measure radians, which is almost never, it's almost never written. It's almost always just understood. Understood. Hey, like if I was to look directly at Chris up here and be like, go to the store. Who was I talking to? If I was looking right here, go to the store. I'm talking to Chris. Now, can you be like, well, you didn't say who should go to the store. No, it's an understood you. Remember that from grammar way back when? The understood you. Have a called an imperative sentence, right? Understood you. Radians are an understood unit. They're barely ever written. Degrees have to be shown. But if there's no unit, it's understood to be radians. So what if they were to give me something like B? I had to convert. B what? B. B what? Radians, because it's not there. If it was degrees, what would need to be there? A degree mark. So if it's B and there's no radians, well, it's understood to be radians. You're like, oh, okay, he's radians. So what would I multiply by? It's on bottom. Why pi? Because pi also has an understood. It's a little awkward when you multiply this direction because the two understood units that aren't really written get to cross out, but nothing else. Sometimes he has a pi, so sometimes the pi gets to go away, but sometimes it's just a number, and you're like, well, that's awkward. Oh, well. The understoods canceled out. And, oh, we need 100. So we would end up with 180 times b over pi. Maybe some stuff can reduce, and it will be in degrees. So that one's degrees. One usually has an understood radians, hence why I didn't box them in the answer. But the point isn't so much memorizing. That's not really the point. The point is, will you memorize? Keep on saying memorize. Will you multiply the correct bridge when the time comes? Hopefully so, to make Mrs. Leon. I didn't want to do that. Proud. Let's get rid of that. Go there. And then go here. All right, kiddos, we're at the end of section 4.1. At the end of section 4.1, I warned you that some things were coming. Physics formulas that say, you know what? You learned radians for a reason. Kind of like 3.5 that I talked about yesterday that said, you know what? You learned exponential logs for a reason. The end of 4.1 says, you know what? You learned radians for a reason. Not just because we want to make your life awful, not just because we think fractions are really helpful to have a mental math understanding of. Not just because we want you to have a way to measure a circle based on the size and not just based on these little tick mark thingies on a protractor instrument. We made you talk about radians because they're the only type of angle measure that can be used in any of these application formulas. Underneath the word applications, you're going to have some more applications on the next page. You only have to really write the title once out here. All of the angles must be in radians. Degrees have nothing to do with the size of the circle and everything to do with how much of a rotation is going on inside. Radians have everything to do with the size of the circle, which we relate to the rotation on the inside. So for all of these formulas that are talking about like actual arc lengths or need some sort of measurement, we have to use radians. Degrees won't make sense and won't work. But that's hard because look at the example. Have you guys already seen it? How do they give you the angle? They're trying to trick you. Don't let them. They're trying to trick you. Don't let them. I'm going to grab up my highlighter to highlight the formula. But as you might have heard me say yesterday, if you were listening carefully, I did not say that the point of this section is to memorize all these new formulas. The same way the point of section 3.5 isn't to fully understand pH levels or radioactive decay or sound intensity or compounding interest. Let's just see if we can do the math. So what's the math say? Do you remember who S is from the other day? Who's S? No, not sine. Size, kind of. He's the length of the arc. He's the arc length. We labeled him yesterday. Who's R? And who's theta? Angle, but in... Okay, so when we come down here and they say a circle has a radius of 4 inches. Cool. Find the length of the arc intercepted by the central angle of 240 as shown in the... Basically, there are a few different ways of doing it, but the most straightforward way is says you want the length of the arc? Fine. Find S such that my radius is 4 and my angle is 240. Nope. What are we going to have to do? Convert. So take 240. What's my bridge going to look like? 180 over pi or pi over 180? Because I need the degrees to... expression, because whenever you just have a number, it's over 1. Can't my zeros reduce? Can't I think of what goes into 24 and 18, and hopefully pretty quickly your brain jumps to 4 goes in, but what's better? 6. And goes into, 4 doesn't go into 18. 6 goes into 24 4 times. 6 goes into 18 3 times. Oh, interesting. 24 is 4 60s and 180 is 3 60s. Radians, degrees. Anyway, that's my radian measure, so that's the theta that I have to use in plugging in over here. Another way of looking at it from the formula that we saw yesterday. Yesterday we were talking about who theta is, who radians are, and their arc lengths over radiuses. Remember our flexible ruler of radiuses? The other way of looking at it is 4 pi over 3. The angle measure for 1 1/3 calzones is going to equal what arc length divided by or cut into 4 inches. Maybe for some of you it's a little bit easier to think about the formula that way. This angle of how many radians the flexible ruler would measure as you wrap around equals the arc length cut into 4 inches, cut into the radii or the radiuses. But either way, you would go ahead and multiply that 4 inches to the other side and end up with the S. So that's just kind of using yesterday's formula. But using today's formula, if you want the arc length, just plug and chug and you end up with 16 pi over 3. And everything in this problem is being measured in inches. As soon as word problems, or I should say application problems come, don't forget to use the units if they come. Inches. Not miles, not feet, but inches. What else are we going to get? But don't worry, the point of the section is not memorizing these formulas, yeah? But what am I going to write as a reminder that you guys don't need to write? This is just keeping on going. More applications. Just keep going. But for your brain to see it yet again, all the angles in every single one of these formulas. Angles? Well, there's one. Angles? Well, there's one. Angles? Well, ooh. This could have angles because S could equal. There's a couple different variations of what could be going on here because we have a formula for S. So we could have an angle. All the radians, all the angles need to be measured in radians. angles and radians can be helpful for something called linear speed. Hey, it's a Greek letter. Which one's the V? What name was that, the V one? Which one was it? VETA? I thought it was new. Is it not new? Isn't it new? Which one are you guys looking at? Oh, you're looking at, yeah, no, it's not that one. Okay. There you go. So linear speed is new. Angular speed, that one's omega, right? The little W. Area of a sector, well, that's simple. It's just like area, like a geometry A for area. Nothing snazzy as far as Greek. But towards the end of section 4.1, they're just saying, hey, we're just going to show you how radians get practical. And radians get practical in these physicsy formulas, geometry formulas, where you have to have radians in order for them to work. So we should be pretty close to having those formulas down. Once again, I'm not even going to highlight them. Like, you're never going to have to memorize them for this class, okay? But I am curious if you can use them. I am curious if you can use them. So for instance, because I don't want you guys getting scared in homework, if you come up against something like this, that gives you, given information, a carousel with a 50-foot diameter. Wait, diameter? We haven't talked about diameter this whole section. But what is diameter? R squared. 2r. If diameter is 50. Radius is used a lot and diameter isn't. 4 revolutions per minute. That sounds like a speed, doesn't it? 4 rounds per minute, yeah. Now hold on. If letter A asks for angular speed needs to be based on angles. Did we write down anything today that had to relate revolutions to angles? What did we write down today? There was something about revolutions and angles, wasn't it? How many revolutions equal, I should put it this way. How many angles, how many radians equal 1 revolution? 2 pi, right? Oh, so if angular speed, if I want to add in angles over time, like that's my units, I'm going to over minutes, radians per minute. I have, how am I going to get to this if I have that? What am I going to build? And what did we say? 1 revolution is equal to what? 2 pi radians? Ah, that'll do it. If I need angles in time or angles over time, change in angle over change in time for angular speed, if I have revolution per minute, I can multiply by 2 pi radians in every revolution. Then all of a sudden I have I and my units are radians, aka angle measure, over minutes, aka time measure. All we had to do was build a bridge for this one. They gave us a speed, just not the right one. Now this is how fast the carousel's turning. This is how fast the angle is changing. And what's letter B asking for? The linear speed in feet per minute of the platform rim of the carousel. AKA if there's a little fly that got stuck on the platform and he's just like holding on for dear life, how fast is he going? That's what's going on. Well, linear speed, isn't it? Arc length. Arc length per time. Well, you know what we can do? We can take our 8 per minute. What kind of measure we want? Oh, feet. Anything that we can do to relate radians to feet? Ooh. I have to think about this one just a little bit. But maybe we need to build a bridge that has something to do with arc length. I'll let you guys play with that one. But that's for the very end of homework. And that's just seeing if you can use the radians to do these physicsy things. Remember, don't memorize the formulas. Don't stress. Just see if you can do it. Bye, guys. See you on Monday. Have corrections ready. I'll be here after school if you need anything.